Okay, I think we're recording. There we go. So let's do a quick review. So hello optics people. This is our virtual lecture for February 9th, 2022, going over lenses. Just a quick review of what we did on Monday. We did a lot of derivation for the spherical lenses. Especially we looked at, say, a spherical lens here where we had a source, we had this object length, and it went to this image length, and it converged here on P. And we used the law of cosines to find the length of this one and this one given these triangles. We found the optical path. We minimized that optical path using Fermat's principle, and we got this expression here. Um, then we said, okay, we're going to do first order parallax rays or Gaussian optics, where we assume small values of our angle. So we're close, A is close to V. So A and A is here, V is here. So the curvature is very large, so this doesn't deviate from that peak very much. And if you do that, the cosine becomes close to 1. Thus, we got this equation here. And this is this equation we're going to use to derive our thin film, our thin lens. And we could find, from this, we could find our focal lengths. So we set all the incoming waves to be parallel. They would focus at this image focal length here. Basically, the object distance would be infinity, which is given by this SO. And then from that, you find that focal length of the image, given here. Here's the radius of the sphere. And then you do the opposite thing, where you set the image to be infinity. So we have a source here, a point source that's giving off rays at this object focal point, and they're all parallel here. So, and you get the equation there. Something got mixed up here, but that's okay. I'll fix that in post. Oh, there it is. F naught da 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 da. So yeah, so our object distance is our focal distance. Then you get this equation here for the object focal length, and then the image focal length. And then we had these different scenarios here where we're at a pretty good distance that converges P. We're at the focal length here. If you're below the focal length, the object focal length, you get divergence, but you get a virtual image at the background. And then you could do the concave of that, where you're at the focal length. So these parallel beams, they diverge. You backtrack them. That's the dashed lines at the focal length. And here, if you had parallel lines here, they would be diverging out, and you front track them here, imaginary, the dashed line, and that'd be at the focal length. There is some sign conventions we need to be aware of, and you can see kind of where these come from. We've kind of talked about these a little bit, kind of played with this. So your object is considered positive if it's on the left, and the image is positive if it's on the right of the interface. So our object length, our object focal length, our image, that's both of those are positive on the left. The image length, the S of I, the F of I is positive if it's on the right. Radius is positive if it's centered to the right. So these guys they're centered here. They have positive, we give them positive radius. This one here, negative radius. So thin lens. So that's what we use in the lab, are thin lenses. So consist of one element, or you can have compound lenses that are consistent of more than one element. So you could have a simple lens that's just a simple lens, or you could bring a bunch of them together into just a single object, or just like a black box of lenses, and that'd be kind of a compound lens. Some nomenclature. So convex is the one that's rounded to the outside. It's called a converging lens also, or a positive lens. They're thicker in the center. Concave, thinner in the center. A diverging lens, because they diverge the light, and is also called a negative lens. And this is how we're going to derive it. We have basically these two spheres of different radius, and then the overlap is going to be our lens. And I said before, we're going to treat it one sphere at a time. So here's our source here, this S. So let's look a little closer. Here's our source. It has these lines coming in here, impinging, and they're hitting the surface of this sphere here with radius r. The radius is positive because the radius is on this side of the board. It's very similar to what we find here, where we have our source is below or less than the focal length, so we get a virtual image in the back. This will make it easy, and we want to find our image length 1 and our object length 1. This we call sphere 1. And you applied the formula we had. Here we're going to call everything that's not the lens the medium of air or water or whatever, and then N sub L is the index of refraction of the lens. And we're just using what we found before here. We're just renaming some things, and this is just because we're just doing this sphere here. We're just doing this case here. Index of the medium of air, index of the lens, and you get this, and we have R1. And that's all well and good. Okay, let's look at the second part. So the second part is this sphere here. And what is happening? Well, this sphere here is seeing this P sub I, right? And it's impinging on this surface here, this back surface. So what it's really seeing, so this is like these beams here are like if this whole sphere were of index N of L, just like this. Because since the last part of the beam was in the material, it's like if you look back down the beam, it's like this dashed line is like the beam was always in the material. So that's what we want to do. This lens to air interface. So our object is in the lens, and this first, our object distance has the index of refraction of the lens, so O2 has the lens. Our image is in air, so it's in the medium, so that's SI2, image 2. And of course you get the difference of the two, so you see there's a different sign because it's the lens, it's the object minus the image, so the object was in the medium, and R2. Now, we've got to be careful of our sign conventions here. So, for one, R is negative. Our R2 is going to be negative. Our object is positive. Okay, yeah, so our radius is negative. We've got to be careful of that. Now let's do some math. So, our object here is essentially, the magnitude of that is the image of 1, right? So we went from here, this is 1, the surface of 1, to here. That's image length 1, plus D, where D is the width of our lens, little d here. So that now this object 1, let's go back and look at this. The object 1 is behind, is on the left, so that means it's negative. So SI1 will be a negative sign using this sign convention here. It's on the left, so it's negative. So the SI1's negative, which we say right here, but the object 2 is positive because the object's on the left for 2. So object's over here with the interface. So if we bring this and bring all that together, well, we know, like I said before, that the object of 2 is just minus SI1 plus D and R2, so that comes object 2, so you take this here, plug it in, you get that right there. This SI2 stays the same, and then we have this here. Okay, and then you just add the two equations. So we're going to add this equation, and we're going to add this equation up. And that's what we do here. Here, this plus this, and we're going to get it in a form like this. So what I did here is I did this equation plus this equation, and I rearranged terms. I wanted all the medium over SO2 and SI2, those all together. Why am I doing that? Well, you can do a couple things. First of all, it's a thin lens, so you can set D to go to 0. So this term here that has all, you see I grouped all the ones that have this length d together right here. So that term just goes away because we're doing a thin lens and we get something. And we can do the medium of error to 1. And if we do that, we get this right here. And this is the thin lens equation. Now, not necessarily the medium's always 1. Sometimes the medium's something else. But a lot of times you normalize your index of refraction of your lens or whatever object's doing the refracting with the medium, and you call it, say, MLM, which is just the lens divided by the medium. And in that case, you just get the same equation out. It just becomes MLN if you do the math. So these two are perfectly acceptable forms of this lens equation. Okay, quick review of what we just did. So we break this into 2 separate spheres. This light source here comes and impacts sphere 1 first. So we do the math there. It has an object distance here, and then this image distance here, SI1, SO1. The image is on the left, so it is negative. The object is on the left, so it is positive, based on these sign conventions in these tables here. And that's well and good, and we get this equation here in yellow. Okay, then the beam has a, from S, from this sphere 1 has an imaginary or a virtual image at P prime. And like I said before, it's like, since we're in the material here at this surface, at this interface, it's like it was always in the surface. So now we can do R2, the second sphere, which is just a solid sphere, because that's what the last bit of beam saw, was just solid lens material here. And we go here. So the object distance is left of the interface, so it's positive. Okay, and we still make the note that the image 1 was negative, but R in this case is negative because it's centered on the left, so it's negative. I bring all these together, we end up with this thin lens equation here or here. Now we do the same thing we do the sphere. So we have this equation or this equation. We're going to stick with this one. We're assuming we're in air. And we're going to set our object. Also, since we have this in terms of, now we have another important thing. We have this in terms of the object 1 distance and the image 2 difference. So this is the input. This is the output, right? This is the final image. This is the initial object where you physically put your object, and this is the final image distance. So these are the 2 things we want to care about, and we're just going to call them S of O and S sub I here, because we now have one lens that has one object distance that we set and one image distance that's set by the lens. So if we set that image distance, or we set our object distance to infinity, then that means our lens will converge, our light will converge on the focal length of the image. And if we do the vice versa, set the image distance to infinity, our object must be a source at the focal length of the object. And if you do that, you see here that if this drops, this one's infinity, you're just left with this thing here. So you end up with 1 over f equals this. And if vice versa. So there's only one f. These 2 f's are the same, because if this is infinity, it's just 1 over f. And if this is infinity, it's just 1 over f equals this. So you can have 1 over f equals this. So these thin lenses have 1 focal length. And since 1 over f equals this, you can just plug in 1 over f on this side, and then you get this equation here, where 1 over your object distance and plus 1 over your image distance equals 1 over f. And this is the Gaussian lens formula. So this is an important equation right here. It's just from there to here. It's just plugging this into here, you get this. And you rearrange and you can get your object distance, which is usually what we want, because that's the thing we're trying to measure, because we know where we set the object. So we need the image distance. So this is S of psi, and it's given here. So here's an example of a thin lens here. So an example, a planar convex lens. So we have a plane, and it's convex here. And the curvature here is like a sphere with radius 50 millimeters. And the index is 1.5. Well, since we have R1 and R2, right? R1, it's a plane, right? Plane has a radius of infinity. And then R2, well, this is centered over here on the left, which means it's negative 50. So we go here and look at our equation here and find our focal length 1 over R, or 1 over F equals 1.5 minus 1, right? Index 1.5 minus 1, 1 over infinity, because it's planar, and then minus 1 over minus 50, so this becomes a plus. This is 0, 1 over 100 millimeters, or F equals 100 millimeters. Now we know F, we can go and find our S, and we can go do pairs. If my object is at 600 millimeters, 200, 150, 100, 500, what is our image just from here? And if you do that, you get 120. See, we have big object, small image. Oh, look at this. We're at 2 times the focal length. Our object and image are the same distance apart. Okay, now we have small object, big image. Now we're at the focal length object, so there is no image. We're at just parallel lines coming out. And then we're below the focal length. We get a negative 100. Right? So if we're, say, below, then this becomes negative. And then that's why we get the minus 50 there. Another note is, once we flip the lens, so instead of having planar convex, once we get convex planar with the same things. So now R1 would be infinity. R2, since it's over here, would be plus 50. So this becomes a plus 50. This becomes a 0. It doesn't change anything here. So the results will be the same. Here's some examples of what we did in pictorial form. So if the object distance is infinity, parallel lines coming in, converge at F. If the object is big, it's greater than the 2F, it's going to be somewhere between 2F and F. If it's at 2F, our object, then the image is at 2F. If it's less than 2F, then it's greater than 2F on the image, so on and so forth. Then you get below F on the object, our image is now virtual coming behind. We can think of also, we talk about the focal point, but it's actually a focal plane. And here, I'll show what I mean here. So here's a light source, right? And I'm going to put that light source right there on the focal point. You see, we get these parallel lines out. So we know we're on the focal point the object is because we get these parallel lines out on the image side. But if I move this up, imagine there's a plane here, straight up and down, up or down. It's always parallel lines, right? So this focal point, this is a focal point, this is a focal point, so on and so forth. It's a focal plane. And you can see we have a focal plane. When we do a spherical, where we have more curvature, it's still a focal. It's a focal plane. It's more of a focal surface that has a spherical that's centered on the sphere's center. But for these guys, the curvature is so small, we can assume a focal plane. Okay. So let's see how much time we have had here. Okay, we've been going for about 19 minutes, so let's keep going. Here we want to make some images, right? So we have our B here. And you can think of your image, each part of your image or your object here, each part of our object is a point source. So we have a point source here at the head. And then his tail would be a point source, his wing would be a point source. So we have these point sources that make up our object. So we have this beam here at the point source. So we're going to say this one beam just goes right through our center and comes out and doesn't deviate. Why is that? So here, and this is very similar to homework 2, problem 2 that you're doing right now, or we have the slab, and we look at this deviation. So really what happens is the beam comes in, there is some bending, and then it comes out, and these two beams are parallel. But because it's a thin lens, this deviation gets very, very small to 0. So we're going to assume that going through the optical axis here right in the center, it's just a straight line. So we have that beam. We can also have a beam that just runs parallel with our optical axis here, hits the lens, and then it's going to converge on our image focal length. That's beam 2. And then we can have beam 3, which goes through the object focal length, hits the lens, and now becomes parallel, runs parallel with our axis here on the image side. So we have these 3 beams, and they can define our image points. Here's the same thing for a convex or concave lens. So send the first one for the center, no deviation, just goes right through. Now, when we have convex, it's diverging, so it diverges, but the back trail is going to go through here, f of I. So you see it's a negative lens, right? So f of I on a converging, or sorry, f of I on a diverging is negative. It's on the left. Go back to our handy dandy chart. If f of I is on the right, it's positive. If it's on the left, it's negative. That's why these are called negative lenses, because their focal points are negative. Image focal point is on the left, object focal point is on the right. So boom, backtrack, and then draw that line. And then this one here, you draw the line right to the focal, or the object focal point. So you dash, 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 becomes parallel here. So you go, it's dashed after here, and it would be parallel after that. So it'd be parallel on this side. And I'll include, even in here in the notes, there's a link to this. I'll include this guy here, and you can play with this. So here we have like our pencil here, so we can see what happens. Oh, see? So we're right at that. We go about 2 times over there. You can play with the thing here. You could also put a second point and see what's going on. So let's do, these are principal waves. Let's make this big. And look, I'm capturing more light. The image becomes better. But I didn't change the curvature. So you see here, this one goes parallel with the axis, hits the center, goes through the focal point. This one just goes through the center of the lens and continues on. This one goes through the front focal point and then goes parallel here. There's our image. Okay, here's this guy. This guy here, right through the center of everything. This guy's parallel, diverges, so it has to backtrack to this focal point, hits there. This is not actually a real beam, that's why it's a virtual image. And then, what's the other one? This guy here comes here, he's in line with this focal point, but once he hits here, he goes parallel, so you backtrack here, and there's our image. And you can move this around. We never lose the image, right? But here, we can get to infinity. Or you can do mini. See there, all those parallel beams at the focal point. Okay. Okay, so we have all that down. Let's look at magnification. So here's an example of what we just talked about, where we have our object SI. We have 2 points on our object, the base and the head of the object of this flower. We call that S1, S2. Then we have the image, P1, P2, same thing. And then we also introduce this X object and I object. So basically it's the focal length plus X object equals the distance of the object. So distance of the object goes from the center of the lens to the object. So it's the focal length plus X naught equals that. Same thing on the image side. We got this XI. And we see there's a lot of similar triangles going around, and I've marked in red the first 2. So we observe that AOF, so AOF, this triangle here in red, is similar to P2, P1, and F. So similar to this image triangle. And you can see that this right here, this distance from O to A is the height, y of the object. So y of the object over this, the magnitude is negative, so we do the magnitude of it, right? Must be the same ratio as f, which is this guy here, over, which is corresponding to this triangle here. So these two, so we do this over this, because we did this over this. So f, which is this distance here, over this distance here, which we called x, or we could call it s, the image distance minus the f. So we keep that. And we could also say, okay, we got S2, S1, O, so this big triangle here, right, is similar to this triangle P2, P1, O, right, because they share this common beam that doesn't deviate. And if that's the case, again, we have our object height versus our image height. It's negative, so we have to do the magnitude of it. And then, since we did this one, so we need our object distance over our image distance. So we ratio this to this, so we can ratio that to that because they're similar triangles. So we get this here. You can combine the two and you can get this. So object over image distance equals f, si minus f. Okay. And then a third triangle, right? Because let's keep going. Let's keep playing with this. So we know here we go S2, F1, focal point object. So this triangle here is similar to BO, F naught. So this triangle here. So this triangle is similar to this triangle. This distance here is this height here, so we'll do this one. So we're going to do ratio of this over this. So boom, 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 boom. And then, so this distance here, so we went, so this has a distance of F. All right, boom, boom, boom. And this here has a distance of boom, boom, boom here. S naught minus F right here. So, and we make the observation before that S object minus F equals X object, S image minus F equals X image. And you can combine these two together, this, and this. You get this, right? Because this is your X object, this is your X image. So you get Fx, you combine them together and you get X object times X image equals focal length squared. This is the Newtonian form of the lens equation. So this is another important form of the lens equation. And we need this for our magnification. And you could have two different magnifications. You can have magnification like this, and you can have magnification along the axis like this. So you have magnification here and here. And look at the time. We're at 28 minutes. So let's look at magnification. Transverse magnification. So how y changes. And it's defined how the image y height versus the object y height. So the ratio of this versus this. So if this is negative, it's going down. So this is going to be bigger than this. So we'll have a minus, say, 1.5. So we had a 1.5 magnification, but it inverted the image, and that's what minus 1.5 would mean. So using this equation here, and so we can see that there's a minus sign going to be thrown in here of this too. So this is our magnification transverse. Or you could look at it this way or this way. And this just comes from these equations here. But I highlighted the one that's important. Longitude's a little different. And here's an interesting little thing here. So all of the object space from 2f out to infinity on the left of the lens, So where we put our object, we can put it at infinity, or we can put it up to 2f distance from the lens, is compressed on the image space between f and 2f on the image side. So let's look at our guy here. So large distance, so 2f's around right there. Let's make our index really small. See, there's not much distance. I can go a lot here, but not much is happening to this image, and that's what that's saying. Let's just do principal wavelengths. Makes it easier. Look at that. A lot of stuff here, not much stuff here. Okay, back. That's the fun aside. Longitudinal. See, does one of these have longitude? No. No. Okay, longitudinal magnification. So in the x direction. So essentially, it's how our image x, or you could do either s of I or x sub I. It doesn't matter. We're going to do x sub I because we have an equation for that. Because it's how it elongates. And both those terms, both x and s, are both going to elongate in the same manner, differential. So we're going to do how this changes the object length versus the image length versus the object length. Sorry if I get those confused. And using our Newtonian form like this, F2, we can just solve this right here, and we can get it this right here. So equals F squared minus X not image, sorry, F squared over X object squared minus equals the longitudinal magnification. And it turns out it's this squared. See, we have this form here of it squared. You might want to go through and do these for yourself, these derivations, and see the algebra and get that. Very nice. Okay, and we're at 30 minutes. So, combination. I think somebody came and erased some of my letters. So virtual object. So an object can be virtual, not just an image. And this happens a lot in your two lens scenarios. And that's what we're going to look at here. So here's two cases. So we have a virtual object. The object here, or no, this is our object here. It's on the right side of the lens. And we have another example here where on a negative lens, the concave lens, it's on the right side. So here's our object. Here's our object, SO, SO. So it's less than 0. So it's real and uptight. So you do the back trace, right, to get the image. So this one here, you have this beam here. You have this beam here, back trace it. So it's going to be parallel here. So this then has to go for here to this focal length. So you back trace it parallel. So it's an imaginary beam here. So once it's on this side, you go, oh, then it goes like this. Oops. So boom, 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 boom. And then you have this one here, which would be stay from here, and it goes, you see how it's imaginary, but it's going to this focal point. So then you go, okay, and then boom, 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 and where they cross, that's your image. Similar thing happening here. Okay, 34 minutes. Let's talk a little about lens combinations. And I'll provide these links. These links should be in the notes. I'll go ahead and post the notes as well for these couple simulations here. So we have lens combinations. So we have an object, we have image 1, and then we had our final image. And we have a focal length 1 and 2. So focal length 2, focal length 1. We can actually play with these a little bit. So you can move this around. You always get an image. Virtual image, you can get a virtual image. Okay. So let's first consider the face where the distance between these two lenses is small compared to their focal lengths. So what you would do here, what we can do here is we have this is our object at S1. And we're going to pretend like lens 2 doesn't exist, and we're going to make that object over here. So we have, see, it's the same thing here, boom, comes down. We have this one, so beam 2 does this. We have beam 1 that comes through the center, and beam 3 that comes here in parallels. And there's our object. So we're going to keep beam 4. I mean, yeah, so beam 4, we'll keep that. Okay, so we're going to keep beam 3. But now it goes here, it hits this lens, so it's going to go to that second focal length, right? So it would have gone parallel, it goes parallel. So now it's a parallel. So now it has to go to this focal length here. So it's parallel here, so it goes here. We're going to have, so that crosses there. Overlooking the two, constructing ray 2. Ray 4 is constructing running backwards from P1. So we have, so let's construct beam 4 here. So we start here, we go backwards, and this is the beam at this point source that goes and hits this guy here, the center of lens 2. So we know if it goes through the center of lens 2, it's just going to keep going straight through here until lens 1. So that's where this beam comes in. And we keep that beam here, and then we get these two crosses here. So let's go over that again because it was a mobile. We're going to construct some beams here, just like we constructed here. Beam 1 goes right through the optical center of the first one. We're ignoring the second lens for now. Boom. Beam 2 comes here, comes over here, boom. Right? It's going through this focal length of 1. Beam 3 goes from here to the focal length of 1, goes parallel, hits here. So this is where the object would be, or the image would be, if there was no lens 2. Now we're going to make another beam from here, but we're going to backtrace it through this center, which is fine because this is like a point object. All these images, all these rays are going to converge here, so we can make any ray we want as long as it converges here. So we're going to make this ray here go through this optical center of 2 and go back here. And once it hits here, we could just draw it going right to the head of the object because we know that's where it's originating, right? This point has to equal this point, so we have beam 4. Okay, we keep beam 4. That's the only one that stays because it went through the center. So we keep that beam 4. We know that's good. Now we take beam 3 here, which came in here parallel, and we know that's going to get diverged to focal length 2 across, and there's our image. If the distance between these two lenses are greater than the focal length, it's the same procedure, but it's actually easier because now this is just, you could just treat this as just another object. This is just the image of 1 becomes the object of 2. And the similar thing happened here. So we have this beam here, goes parallel, goes through here, and then bounces over here. Okay, so beam 3 hit the focal length 1, goes parallel right here, and goes focal length 2 onward to the final image. Right? Boom, boom, boom. You backtrace. So you take here, you have a beam that goes through the center of O2 like we did here. You don't have to backtrace it. You go forward propagate it from here to this, and we get our second beam here. So it's easy to get this guy to this guy, and then this guy to this guy. It's kind of complicated. If you look at it, you can understand it. We're not actually doing any math right here. We're just using our focal points as guides. So we take our image from this guy. We draw from there to the center of the second lens and keep going. And really, we don't care about this part here. We actually don't care anything about beam 4 below this because this is the only part that really matters. Then we keep this beam here. The other beam that's really helpful is this beam here, which goes here to 3. So it goes through the focal point 1, hits here, and goes parallel. So it's going parallel, so it has to go through focal length 2 when it crosses here. So we have these two beams, they converge. So what's going on with this beam 2? It's kind of doing something funky. So it's here. We know it's going to cross here. It crosses here. So it here. Okay. So how do we get this? We'll probably use some kind of ray tracing to get this one. So we're going to kind of ignore beam 2 for now. It helps us get this object here real easy, but it's kind of a little less obvious what's going on here on this side. Once we get these two, we can converge it. So if we had a parallel one, so if this is a source, every beam, so every beam here, oh, okay. So if I had a beam here, it'd be parallel to that. Yeah, we just gotta ignore that for now. Okay, so let's actually do the math on these things. Because we just did all this stuff, let's do some math. So we're gonna use our lens equation here for lens 1. So 1 over, so this is just this guy rewritten. Right. Yeah, this guy right here. We're going to rewrite this guy here, the Gaussian wave form for lens 1, and we get this. All we're doing is mixing terms around, and this is all image 1, object 1, focal length 1. Or you could, image 1 is this. Now we're going to consider, this is just looking at lens 1, looking at lens 2. Well, we know that the object distance of lens 2, right? Look at this one. Object distance here to here, from here to here, is this distance here, minus the image distance. Because the image of 1 is the object of 2. So we have that. Now we just do this form for lens 2. So image distance 2, focal point 2, object distance 2, or this. We can plug in this guy here into here. So that became that. So there and there becomes that and that. And now we plug this, because look, we can plug this into this. Gets messy, and we can get this here. So we have image 1 here. So we can plug this. Okay, let's plug this into this. Right, this into this, and this into this. And we can get this. Because what we want is our final image distance, which is image distance 2. And we get this mess equation, but it's only in terms of our input, object distance 1. So all we need to know is this distance here, and we can get this distance here using this. Yeah. And then our total magnification, transverse magnification, is just going to be the multiplication of the two magnifications, which can be written, if you go and do some algebra, as this right here that I highlighted. So another way to do some ray tracing here is focal plane ray tracing. So remember, let's bring up our handy dandy. So remember, let's make our optical. So let's make our focal point come over here, and we'll do mini rays. So remember, if you're at a point here, if you're at your focal point, the beams past the lens are all parallel. But you could have a second point, say over here. Again, all these beams are going to be parallel. So wherever the source is, so this is a point source, and this is a point source. If you go from here, here, it doesn't matter where it goes as long as it hits that lens, it's going to be a bunch of parallel beams, and you can use that. So say for this lens here, we're going to have this guy here, A. So I draw A to B, that's a ray, or A to O, that's a ray. Well, A to O just keeps going. So whatever pops out here has to be parallel to this guy here. So A to B, you know it's going to be this. And then I draw this one here, so some random place, and it has to be parallel. So all three of these have to be parallel, right? And we can get the distance, or get the direction from that center beam, from going here to here to here. So we know that's there. Can we use that for beam 2? Remember this stupid beam here. So maybe, so this is, so this right here. So what we'll do here, we'll go back to this example here. We'll draw a line. We'll make that line actually, yeah, we'll make it blue. So we'll draw a line. Oh. I want my line on F2. Ah. Oh, come on. Let's try that again. Oh, well. Well, let's just physically draw the dang thing. So here's this example here. Here's F2. So we go up and so this can be considered a point source. So can I go here to here? That seems to be a right angle. Well, never mind. It has to be on this side. There's sign convention I'm missing. Let's go back to this because everything's on the left here. So we have we're on this focal plane. This is our source. Yeah, this is a source. So we need it on the object side. That's why that messed up. So we're on the object side. So we're on the object focal plane here, and these are all sources. Wherever they cross, they all have to be parallel on this side because they're on the focal plane. So A to B, so this one's the guide, right for the center is the guide, and they're all parallel. Okay, let's do it over here. On a negative lens, a concave lens, this is the object focal point. So this beam comes in here, its imaginary part goes here, so this is its source here. So this is our source. So we can go here and draw this line, this beam here, which propagates this way. Oops. So it propagates like this. So now we know this is our guideline, and we know this and this have to be parallel, so we can go ahead and draw our B ray. And if you have a bunch of lenses together, you can do this. So we're at a focal point. We're going to set this guy A. So we want this beam here. We want to track this beam through everything. So it crosses the focal point here. So we'll call that a source. We'll draw an imaginary beam from here to here. And that keeps going. So this has to be parallel to this, right? Because it comes here and becomes this. So this keeps going. So this is parallel to this, right? Boom, boom. Now we're at a negative lens where we have to look at the focal point here, which is focal point 2, given right here. So we're going to keep going. So this guy keeps going, hits here, and it's the blue source now, because this is where that focal plane is. Boom. Okay, we want the center one, so we're going to backtrack from here, here. So this has to be parallel with this. So you can kind of see they're parallel. Slash. So this crosses the third lens here. So this is our source A3. And we can treat it just like this one. So we can draw the imaginary line through the center. So this line has to be parallel to this line. Okay, a few more minutes. A combination lens. So we have this optical system that has these two lenses together, which is what we were doing here or here. We want to kind of see what the back focal length is. Imagine we don't know what's here. We want to know the back focal length, which is this focal length here, and the front focal length, which is this focal length over here, whatever. And we're just going to consider there's two lenses here. So from lens 1, we're going to take, remember we're doing this right here, we're going to take our Gaussian lens equation from this one, and our Gaussian lens equation from 2, and then this linkage here. So to find the front, well, we're going to set the image of the whole system, the final image distance to infinity, which means object distance equals f2. So from this, object distance equals this minus this, has to equal f2. So our image distance 1 is d minus f2. You plug this in for this, right? Boom, boom. So object distance, and you rearrange your object distance when our image is at infinity equals 1 over the first focal length, d minus the second focal length, which equals this here when you combine the terms, which is the front focal length. So this focal length over here for this system. And we inverse this, we get this. The back focal length is the same scenario. We set the input object, object 1, to infinity. That means image 1 is at focal length 1. That means object 2, because we're using this linkage here, is this, which is d minus f1. So we do, now we plug in for here. Object goes into infinity, this. So we have the f1 over f. Plug this in here for that. Get this, and we get this, and then we get the back focal length to be this. Now we have the front focal length, the back focal length. If we bring the lenses into contact, d goes to 0. If we bring these really close together, look what happens. This d, and this d, this d. We end up with this here. Or the total focal length of the system is just the inverse sum of them. So if we have multiple, like 3 lenses brought really close together, you could be plus 1 over 3, 1 over 4, so on and so forth. But that only really matters if their d goes to 0. If not, we have to be more careful. So that's why we only did 2 here. It gets a little more complicated. Okay, that was everything you wanted to know about lenses. I'm a little over time. I'm going to post these notes. Please go over them. We'll need this for the lab. At least understand to here. The combination gets a little more difficult with the ray tracing. You don't probably need the combination. We'll do a combination, but it probably won't be necessary to understand that fully. So at least get this first part down for the thin lens. Let me know if you have any questions. I'll be gone all day tomorrow, but I should have some email access. And when my son's taking a nap, I'll try to answer some emails. Please take a look. I'll also post a link. Well, it's in the notes, but I'll post a link to this simulation and these guys here, where you have this one or this one to play around with. All right. Thank you, and see you guys later.